In this lecture, I will be discussing about certain practical signals, and then I will give you a demonstration of few signals which occur in practice, and look at them in both in the time domain as well as in the frequency domain on the run. So, as you would have seen, or by now we would have realized that the signals can be continuously periodic or they can happen only once and that is it. So, this is a stationary signal, and the definition of stationary signal is that the time domain ensemble properties of this packets of the signal do not change with time, whereas in this signal you would have seen that the values change, which is not true in this case, and so on. Okay. And some of the stationary signals which are there are sine waves, square waves, sawtooth waves, triangular waves, and some of the random noise. So, I will describe to you, for example, here I have a signal generator wherein I can generate a sine wave of 1 hertz of 1 volt amplitude, peak amplitude, and 200 hertz. I can just stop the stores. So, this is a sine wave, okay, where the delta t is 195.3 microseconds. Okay. For example, I have about 2,400 lines. So, 2.456 about 1024 points. So, if you will see, this total time is about 0.2 seconds. I can change the number of lines to 800 and this will become double. So, I have taken in more data points, okay, and I am taking in now more data points. If you notice here, this is the total time in seconds, 0.8 seconds with 1600 lines. If I half it, 0.4 seconds. If I further reduce it, 0.2 seconds. Okay. The reason behind that is I am taking the values of n as 1024, make it 2048, make it 6400, and so on. Okay. You can see for 3.2 seconds. I will reduce it right now. So, one can play around with the number of data points. I can further reduce it, and you see this is a sine wave of about 1.1 volt peak amplitude. One volt peak amplitude. I can measure it through a cursor here. This is about 1.004 volts. See that point? So, I am generating for 2000 hertz or 200 hertz a sine wave of 1 volt peak amplitudes. Okay. And then I will go to measurement. I can stop it. I can now generate a different waveform types also. Okay. But one thing which you noticed here is we have not changed what I have done here is my t is n times delta t, or nothing but Fs by n. I have kept as Fs as 1 by delta t, that is 1 by 195.3 10 to the power minus 6 seconds. Okay. And all I have done is varied n from 1024, 2048, 4096. So, t is proportionately changing. So, when I have n is equal to 256, it's 0.04, 4 times it becomes 0.2. So, 1024 points, this becomes 0.2 seconds. Okay. So, you can in fact find out delta t in another way also. Delta t is nothing but total time by n. So, total time is 0.2 seconds and n is 1024, okay, approximately 0.2 10 to the power 3 hertz seconds. Okay. And then Fs is nothing but so delta t is .2 milliseconds, okay, close to, or 0.195 milliseconds, 0.2 milliseconds. If delta t is 0.2 milliseconds, Fs is 0.2 10 to the power minus 3, 1000 by 0.2, 10,000 2, close to 5000 hertz. So, I am sampling at 5000 hertz, which I am not changing. All I have done is, so you can find out the delta f is nothing but 1 by t, that is 1 by, in this case it is 1 by 0.2, that is 10 by 2, 5 hertz. Okay. We will see that once we do FFT for n is equal to 1024. So, just to give you an idea, I will change this again to 800. This becomes 0.4 seconds. Okay, let me, and delta t is not changing. Now, I will go to a square wave. So, this is the same square wave of 200 hertz, okay. And the reason you see this glitches here is because I do not have infinite terms. Because the way this is being constructed is summing up a lot of sine waves, and then you will see this is also a periodic stationary wave of 1 volt amplitude and 200 hertz. This is another triangular wave. Okay. All right. I'll go to random noise. So, this is a random noise which is happening, okay, of certain RMS value 0.0537. I can increase the RMS value. So, the value is very, very high, 2.07 seconds, 2.07 volts. So, I can play around with the voltage of the source by changing these frequencies. Okay. So, these are examples of some of the stationary signals. I can have a DC value where I can give a 1.3 volts. It is time for the filters to settle in, for the gains of the amplifier to settle in. That is why you see this jumping around, but eventually this is going to settle down around 1.3 volts. Okay. I will give you a pink noise here of 0.755, okay, a white noise, and so on. The burst random noise. You see this 50% period. If I can change this to 25% period and so on. Let's see what happens if I make it 100%. Yeah, obviously you will not. I can make the burst by having 75% of the time period as burst, and then remaining 25% is lull. So this is a burst random. It's a good example of a non-stationary signals, because in stationary signal we would have assumed that this is true for all times, but which is not sure, not the case here, because there is a no signal here, and that is a burst random with 75% period, and it has a certain RMS value. I can generate an impulse chain, quiet zone, active zone. I can reduce it. Quiet zone in seconds, 5, and active zone. So these are all impulses. Okay, I can make the active much smaller. These are all impulse trains which I have generated. Okay, so these are examples of non-stationary signals. Okay, I can generate a sweep sine, wherein the low frequency is this much. I will reduce the high frequency, and then sweep rate can be I will make it less. So you see this in the same time window, 0.2 seconds, I am having the signal frequency go from 200 hertz to 1000 hertz. Okay, I can further reduce it. Maybe make it a little more. So these are all sine wave of certain amplitude, 1.2. Amplitude is not changing, peak value is 1.2, but the signal is increasing from 20 hertz to 800 hertz at a rate of 0.25 seconds per sweep. So these are a few examples of actual practical signals which have been generated in the case of with a signal generator. Now we will see how these signals look in the FFT domain. So let me change the signal, go back to my sine wave, and we will see. I will make this as 1.0. So I have generated a sine wave wherein of 1024 with a sampling frequency of so let us see what happens in the FFT domain. So I look at the bottom window here, and if I move the cursor, let's say the magnitude, and I will change the units to RMS. Okay. So you see here, to begin with, I have generated a 200 hertz sine wave of 1 volt amplitude, which you can see here if I move the cursor this cursor here close to 1.005 volt or 1 volt peak, right. Now, what I have done, if you go to the measurement, I have taken 1024 points, and if I come here to the frequency domain, my delta f right now is 135. If I move it, next point is here. So, every 5 hertz, okay, I have delta f is equal to 5 hertz as per this equation here. Delta f is 1 by t, 1 by 0.2, that is 5 hertz. Okay. I can improve, and of course, let me go back to 200 hertz here. So, 200 hertz, I have RMS as 0.707, because I said A RMS is nothing but A peak by root 2, that is 0.707 A peak. I have generated a sine wave x is equal to A sine 2 pi f t, where A is actually 1 volt, sine 2 pi f is 200 hertz t, and so A RMS would be nothing but 0.707 volts is what I am seeing at 200 hertz in the bottom curve here. Right. Now, I will demonstrate to you in the last class which I told about picket fence effect. Imagine if I gave a value of 202.5 hertz sine wave. Okay. So, let me go back to my waveform source and make it 202.5, and I have started the source. You see, if I move the cursor here, you see, I quite not getting at, because 185, 200 it is giving me a value of 0.606, 205 it is giving me 0.606, and 210 it is coming out. So, I know the value is somewhere between, if you can closely see here, it is almost a horizontal plateau. Okay, because my delta f is only 5 hertz. If delta f was 2.5 hertz, I should be able to catch it. And how can I change that? I will just go to my measurement and increase this to 800. Okay. Now, you see it becomes 800, then this becomes 0.4. So, delta f would become 1 by 0.4, that would become 2.5 hertz. Now, let me see, if I do the measurements, you see here it is 87.5, 90. So, I have got delta f as 2.5 hertz. So, if I come close to 200, see 200, 0.358, 202.5, I have got 0.707, and this is what I have demonstrated to you as a picket fence effect. Okay. I could have done the windowing. I have used a windowing function Hanning. I could use different types of windowing functions here. Okay. Maybe I will use flat top here. In this case, it may not show me much difference, but let me see. Point 7123. It's usually best to stick on to Hanning. And there are different types of. Okay. Now, we saw this in the sine wave. So, we just saw what we saw was different types of signals being generated, and then we saw the case of sine wave. We showed you FFT, the frequency domain, and because this is a single frequency signal, you only saw one frequency. I demonstrated to you the effect of delta f being small or large, and how by changing the value of n we could change the delta f value. And now what I am going to do is go back and measure for the case of a sine wave, for a square wave. So, square wave of 1 volt amplitude, okay, and I will make it 200 hertz. Yeah, I got a square wave here of 1 volt peak amplitude, and then 200 hertz is the fundamental frequency. If I go to the measurement here, in the bottom screen here, you will see I have got an amplitude of 200, a certain amplitude, and I can move the cursor here. At 200 it is 0.849 hertz. For a square wave, one volt peak amplitude of 200 hertz. Okay, I have seen that at 200 hertz, this is 0.8449 volt RMS. The next harmonic is 3 times that, and that is at 600. So, square wave essentially is made out of sine waves of different components. At 600 hertz, 3 times omega, it is 3 omega omega or f. It is 0.163 volt RMS. Then I will see at 5 omega, that is 1000 hertz, and so on. This goes to all the odd harmonics till about infinite. Okay. At 500 hertz, 5 times 1000 hertz, I have an amplitude of 0.0243 and so on. So, if you look into the Fourier series of a square wave, you will see this is a certain a or certain x, okay, then 3x, 5x, and of course, x by amplitude will be x by x, x by 3, x by 5 and so on. So, this will be approximately somewhere around that figure, okay, and then VRMS, so on. So, square waves, we can see the FFT. Now, if I change the waveform source, now let me go back here, change the frequency here, make it 100 hertz. You see, there will be many components, 100, 300, 500, 700, all the odd harmonics are there, and the amplitudes also decrease, and this goes all the way till infinite. Okay. So, this is the frequency domain representation of a square wave. Now, let me change the waveform type, let me make it triangular, and for triangular you get its frequency content and so on. Let me make it a random noise. Now, interestingly, in a random noise all frequencies are present. Okay, you will see here, and if I can do an averaging here, I can increase okay, it will do an average, and then I will get the frequency domain signal. Now, if you go to the chirp signal, you see because the frequency has changed, you will see frequency has started. I can start again. See, this is a good example of a non-stationary signal. If you look here, the amplitude is almost same. Okay. And then frequency is increasing, decreasing, again increasing. So, we will go all the way from 0, it has gone up and then again come down. So, there is a lot of frequency smearing. So, this is a non-stationary signal and this is a FFT signal, FFT of that, assuming that it is a stationary signal, and this is quite not right, the right representation of such signal, okay, because this says, you know what, a frequency of 400 hertz of maybe 0.07 amplitude exists at all times. That is not true here. So, we need to do what is known as a time frequency analysis of such signals. For non-stationary signals, FFT is not to be used, rather a time frequency analysis is to be done, like wavelets and so on. Okay. So, I had shown you certain non-stationary signals, like a chirp signal is what we have it on the screen here, okay, or an impact where I had changed the duty period. Okay. And so, a real world signal from a machinery is actually a combination of all these. This is a real world machinery signal, and later on in the classes you will see any transducer I put on a machine, I will get such time varying signals. So, we have to do an analysis as to how do you find out the frequency content of these signals. Okay. So, you saw the effect of how this frequency can be changed in such signals and so on. Right. So, more examples of this you will see in my book, and particularly to finding out the features of some of these signals in the time domain, and also to see how these FFT can be done and so on. Thank you.